Hello and welcome everybody. Today in calculus, we're looking at I guess kind of like a day three for separable variables. Where you're looking at applications of word problems that deals with these types of differential equation. So the specific type that we're looking at right now is going to be something I guess called rate in minus rate out. There's really no particular name for it, but that's just the general idea behind it. So I'm just going to go ahead and coin the term and go ahead and give it a name then. Okay. All right, so here we go. Let me go ahead and clean this up first. Okay, so here's the problem. It says the air in a room with volume of 180 cubic centimeters or cubic meters contains 0.15 carbon dioxide initially. Freshly air with 0.05% of carbon dioxide flows into the room at a rate of 2 cubic meters per minute, and also it's mixed with the airflow out at the same rate. Find the percentage of carbon dioxide in the room as a function of time. What happens in the long run? Okay, so there are a few information that I need to get from here that will allow me to come up with this differential equation and hopefully then be able to solve for it. So the first part is that I noticed that we're going to have to solve for a function that deals with percentage. So I'm going to go ahead and call that P of T. And that is going to be represented as percentage of the CO2 that's in the room over time. And the time is in terms of minutes. So that's from the last sentence over there before the question. Then from the very first sentence, we're told that we have an initial amount of CO2 in percentage, which is going to be 0.15%. So that is going to be our first part. So note that P, just to kind of like write it out on the side right here, has to never exceed over 100 then in this case, because P represent the percentage. Okay, next in the middle, they're telling us what's the rate going in and what's the rate going out. So the rate going in is supposed to be the 2 cubic meters per minute, and also the 2 cubic meters per minute going out at the same time. So going in and out the room, you basically have the same rate in terms of cubic meters per minute. Now that right there is going to be a problem because you'll notice that all of these things that are given to me, they are not exactly related because the rate in minus rate out thing, well, for one thing, that's going to give us 0. So how does that actually works out? And how do we implement the whole, the amount of carbon dioxide that's going to be in the room also? Like how much percentage is all going to go in? So let's go ahead and try to put all this together and see if we can come up with a differential equation then. So as I said first, what we're going to have to do is we're going to have to look at this as the following. We're going to have to look at dPdt, okay? And dBdt in this case represents the percentage of carbon dioxide that's in the room that is at a certain rate. So sorry, let me be a little bit more specific. dPdt represents the rate of which the percentage of carbon dioxide is going to enter / exit out of the room, the total rate basically. Okay, so as again, I'm going to go ahead and write it as rate in minus rate out. Now, the unit for this to help us figure out what this is going to look like is supposed to be the percentage per minute. Okay, because, well, as we said, P represents the percentage, and then T is the time, and that's in terms of minute. Now, if we go ahead and apply what we're given here, then that means the rate going in, there's going to be the 2 cubic meters per minute that is going to be involved. And then at the same time, there's also going to be the 2 cubic meters per minute that's going to be involved over there as well. There are some parts that we need to add to it because remember the unit has to be in terms of percentage per minute. They tell us that when you're going in, the fresh air is going in the second sentence right here. Let me go ahead and kind of highlight it. Fresh air with only 0.05 percentage of carbon dioxide goes in. So then that means that I can take this rate going in and multiply by that right there, which is going to be 0.15 in this case, right? I think that was it. Oh, no, 0.05. So let me go ahead and change that right here. Okay. And that right there is going to be in terms of percentage. So let me go ahead and write that in there. So technically right here, that was part of the rate in. So I just didn't write that down, and that was my fault right there. Okay. Okay. So now if you look at the two right here multiplied together, it still doesn't quite make sense because the rate in minus the rate out, it is going to be in terms of percentage times the cubic meters divided by minutes. And then over there on the right hand side, the rate going out, and I need to write the rate going out over here, okay? The rate going out, well, that has to do with the amount of carbon dioxide that's also already in the room. So that means that there has to be a P in that equation right there. Okay, so remember, when you're going outflow, right, you're going to take some of the carbon dioxide that's with you, and in terms of how much of it, well, it's the amount that's actually going to be in the room, and that's why that P is going to be there, and that is going to be in percentage. Now, keep in mind that I need to make the units into terms of percentage over minute, and I need to get rid of that cubic minutes. And that's where the hidden part comes in, because this is where the initial part where it says that you have 180 cubic meter comes in. That right there acts as kind of like your density that allows you to figure out, to put all this together. So if I take my 180 cubic meters and divide both parts of it by it, okay, and then you can see now in terms of the units that the cubic meters are going to cancel out. The cubic meters are going to cancel out, leaving you with the percentage per minute that we're supposed to get. Okay, so let's go ahead and see if we can clean up this equation a little bit so you can see what it looks like then. They both have 180 in common, so I'm going to go ahead and pull that out. And the first part, it's going to be 0.05 times 2, which is going to be 0.1, or I can write as 1/10. Minus, for the second part, is going to be 2p that's going to be left over because the 180 is going to be factored out. And again, the unit in this case is going to be the percentage per minute. So this is very similar to the what's that called? The volume and the force and also the mass and all, the density type problem that we did in the past. We have to look at the units in order to figure out how to solve for this differential equation or set up this differential equation. So all of that is equal to dp dt. Now we can go ahead and separate the variables and hopefully solve for this then, okay? But before we do so, maybe we can do a little bit more cleaning just to make it a little bit easier. I noticed that for the inside, I'm going to go ahead and factor out the 1/10 just to make it so that I have no fractions whatsoever in there. So 1 over 1800. And then multiply by 1 minus 20p, and now I'm ready to go ahead and move the stuff over from the left and to the right to do the separable variable thing. So dp divided by 1 minus 20p is equal to 1 over 1800 and then dt. Now, just in case you don't see it, we're supposed to technically use a u substitution for 1 minus 20p. And so du is equal to negative 20 times dp dt. But just to kind of kill a little bit of time, just to make it a little bit faster, because it helps to do this, in the future when you're doing these type of long problems. The left-hand side, you should be able to recognize that that's going to be natural log of 1 minus 20p. And because of our u substitution, then that means that there should be a negative 1 over 20 that's being produced because of the reverse chain rule. And all of this is equal to t divided by 1800, and then we have plus c. At this point, I usually like to solve for what c is equal to, so then that way we can see more numbers than variables if possible. So p of 0 is equal to the initial amount, which is the initial percentage that's in there. So in this case, that's going to be 0.15 then. Okay, so we're going to take that and plug it into the equation. So negative 1 over 20 multiplied by the ln of 1 minus 2 multiplied by 0.15 absolute value, and then is equal to 0 divided by 1800 and then plus c. And you can see hopefully now that this is where that absolute value makes a difference in the natural log, because otherwise we wouldn't be able to solve for this. Negative 1 over 20, ln of 1 minus 20 multiplied by 0.15. That's like saying what's 15% of 20? That is equal to 3. So 1 minus 3 right there is equal to c then. And as I said earlier right here, you have a natural log of a negative number. So thankfully we have that absolute value there. So c is equal to negative 1 over 20 multiplied by the ln of 2. Okay, plug it back into our equation. So 1 over 20 negative multiplied by the ln of 1 minus 20p is equal to t divided by 1800. And then we're going to go ahead and substitute c in there, which is 1 over 20 negative times the ln of 2. Do a little bit of more math, and then we're going to be done. And focus, remember, we're trying to solve for what p is equal to over here. So we need to isolate that all by itself. So first, I'm going to go ahead and multiply everything by negative 20. So ln of 1 minus 20p is equal to, let's see, that's going to give us negative t over, looks like 90. And then this part, the next part is going to be plus ln of 2. Get rid of ln by taking the log of both sides, or not the log of both sides, by taking the exponents of both sides. So 1 minus 20p, absolute value once again, is equal to e raised to the power of negative t over 90, and then plus ln of 2. And this, when we have exponents added together, and one of the exponent is a natural log, it is good to split them up. So we get e to the negative t over 90 multiplied by e to the ln of 2. And this part right here, e ln of 2, that is just equal to 2. So then that cleans up to be something very nice and clean, which is 2 multiplied by e to the negative t over 90 then, okay? So let me go ahead and make that 2 look like not a z, and hopefully we can finish this up. Let's see, get rid of the absolute values. So 1 minus 20p is equal to plus or minus 2 multiplied by e to the negative t over 90. Let's see, I need to solve for p, so I'm going to go ahead and put p on the other side and then put the other part onto the other side. So 1 minus plus 2 multiplied by e to the t over 90, because I'm moving it over to the left-hand side, is equal to 20p. And it doesn't matter if it's plus or minus plus, because we're going to go ahead and have to choose one of those in a little bit. So the final setup is that p, which I can write as a function of time, or p of t, is equal to 1 over 20. And then I'll just write it as plus minus because it seems more natural this way. 1 over 10 times e to the negative t over 90 then. And right there, that is going to be your equation that tells you the percentage of carbon dioxide that's going to be in the room over time. Now, the last part is that they said, I want to find out what happens in the long run. So meaning as t approaches towards infinity. So meaning that if you let this whole thing sit, I want to know how much carbon dioxide is going to be in the room. So they want us to solve for the limit as t approaches towards infinity of p of t. Well, you can see that the first part is going to be just 1 over 20 because that's not affected. And then, oh, wait, actually, there is a little bit more that I need to do. I do apologize for that one. We need to take care of the fact about the plus or minus that's over here, right? No, let's just go ahead and think about it logically. If I take a plus, I will have 1 over 20 plus 1 over 10 e to the something, and that looks like it's okay. But if I take 1 over 20 minus 1 over 10 times e to the something, potentially this could be a negative number, and that doesn't make sense. So, and the reason is, well, we have this as a percentage. So by logically, then we can say that we should be able to take the plus instead of the minus then. So our equation, just to clean it up one last time, is going to be 1 over 20 and then plus 1 over 10 e to the negative t over 90 is equal to p of t. So that's our brand new spanking equation then. Okay, so that's the most cleaned up one that we're going to take. Okay, but now we're going to go ahead and do what we said earlier, which was to look at the limit as t approaches towards infinity. So as t approaches towards infinity, what will happen is that you will still have the first part, which is 1 over 20. Now the second part, you'll have 1 over 10 multiplied by e to the power of negative infinity, which is going to go to 0. So that leaves us with just 1 over 20. So that is equal to, let's see, that's going to be 0.05 then in this case. So in the end, after everything is cleared, then that means you're looking at the room is going to kind of stabilize at 0.05 of a percent of carbon dioxide that is going to be in the room then. So in terms of how does it reach, how does it go into what happens initially? The initial amount is 0.15, and then the over time amount is that it's going to be reduced to 0.05 in this case. All right, well, there you go. Thank you so much for watching, and hopefully you learned something out of this. I will see you guys next time. Take care. Bye-bye.